The next section we're going to look at is actually the Pic Architecture and Assembly Language Programming. This is our introduction to some of the commands and the structure of the commands, what the syntax looks like when we start to tell the Pic 18 what we want it to do, make it do something useful. In each of the sections that we're going to look at the working register, the WREG register, in the PIC, the PIC file register using instructions to default the access bank, the PIC status register, the PIC data format, and the directives which define what the data format looks like. An introduction to PIC assembly programming, assembling and linking a PIC program, the program counter and the program ROM space in the PIC, that RISC reduced instruction set architecture that we use in the PIC, and then viewing the register and memory using the MPLAB simulator. As we go through this, you can see we've got several objectives, to look at as far as this section. Examining the data RAM, manipulating data using the working register in the move instruction, performing simple operations such as add and move, explaining the purpose of a status register, discussing data RAM memory allocation, a list of the special function registers of the PIC. We learned to code some simple PIC assembly language instructions, describe the PIC data types and directives, assemble and run a PIC program using the simulator MPLAB, describe the sequence of events that occur upon PIC power-up, examine programs in PIC ROM code and explain PIC ROM memory map, detail the execution of the PIC assembly language instruction, understand the reduced instruction set and the Harvard architectures of the PIC microcontroller, and then finally examine the PIC's registers and data RAM using the MPLAB simulator. As we proceed through the information, we're going to start learning and categorizing some of the instructions used by the CPU to execute commands. PIC microcontrollers have many registers for arithmetic and logic operations. Among them, the working register, because there are a large number of registers in the PIC, we'll concentrate on a widely used register called the WREG, or working register, for this section. General purpose registers are also covered in this section, as well as the special function registers, and these are those registers that we categorized as the GPR and the SFR registers. So we'll look at the working register first and learn something about a couple of commands, the move and the add. And it's just a matter of using those commands to move data into this accumulator, this repository called the working register. In a CPU, registers are used to store information temporarily. That information could be a byte of data to be processed or an address pointing to the data to be fetched. The vast majority of PIC registers are of the 8-bit type. In the PIC, there is only one type of data. That's the 8-bit. The 8 bits of a register are shown diagrammatically, and we'll take a look at that, with their range from the most significant to the least significant. And this is what the diagram normally looks like. The 8-bit register is the most widely used register in the PIC microcontroller. WRG stands for working register, and there is only one. This is the only place that you're going to move information in and out of temporarily to get the data to the registers that you want them to finally reside in to take action on them. The working register is the same as an accumulator in a microprocessor. The working register is used for all arithmetic and logic functions, and to understand the use of the working register, we'll show it in the context first of two very simple moves. or programs, instructions called the move and the add. So the first one we're going to look at is called move LW instruction, and it's a move of a literal value, and the W stands for working instruction. So simply stated, the move LW instruction moves an 8-bit data into the working register, and it has the following format: move LW, K, which is a value, semicolon move, and the literal value that we're looking for of K into the working register. K is an 8-bit value that can range from 0 to 255 in decimal, or 00FF in hex. The L stands for literal, which means literally a number must be used. In other words, if we see the word literal in an instruction, we are dealing with an actual value that must be provided right there with the instruction. This is similar to the immediate value we see in other microprocessors. Notice that the move LW, the letter L comes first, and then the letter W for working register comes next, which means move a literal value to the working register as the destination. The following instruction loads the working register with a literal value 25H. Okay, so we've got a value of in hex 25 that we want to move. So in doing this, we set up the instruction code so that move LW 25H semicolon move the value 25 hex into the working register, and it will equal 25 in hex. The following instruction then loads the working register with the value of 87 in hex. Move 87 hex, load 87 hex into the working register 87H. And then finally, the following instruction loads the working register with the value of 15 hex, okay, and 21 in decimal. Move LW 15H, move the value 15H into the working register 15H. So all we've done is we've gone through, given some instructions to move values 25, 87, and 15 into the working register. So next we'll take a look at adding a literal into the working register.